Hello, calculus people. We're starting a new unit now on the applications of integration. And our first topic is going to be finding the average value for integrals. First, a review of the mean value theorem. The mean value theorem said that if f is continuous on a closed interval ab and differentiable on the open interval ab, then there exists a number c in AB such that f prime of c equals f of b minus f of a all over b minus a. Oh, so many words, so many letters. In other words, somewhere the instantaneous rate of change at c equals the average rate of change between a and b. Or you could also say that somewhere the slope of the secant line equals the slope of the tangent line. We have a similar concept with area under a curve. The area of a region under a curve is greater than the area of an inscribed rectangle and less than the area of a circumscribed rectangle. What does that mean? Well, if you look at the figure here, we have this curve and we've made this rectangle here to estimate the area of it. But on the left-hand side, the rectangle overestimates the area under the curve, and on the right-hand side, the rectangle underestimates the area under the curve. But in between those, there's this perfect little spot where the height of the rectangle is right where it needs to be. The mean value theorem for integrals states that somewhere between the inscribed and circumscribed rectangles, there's a rectangle whose area is precisely equal to the area of the region under the curve. So the mean value theorem for integrals, if f is continuous on a closed interval ab, then there exists a number c in the closed interval ab such that the area under the curve equals f of c times b minus a, where f of c, that's the average height, and b minus a is the width of our interval. Now you can solve for f of c by dividing both sides by b minus a, because this f of c we're really curious about, so we want to isolate it. And this brings us to the average value of a function on the interval. If f is integrable, I always struggle with that word. But anyway, if you can integrate f on the closed interval ab, then the average mean value of f on the interval is 1 over b minus a times the area under the curve. In other words, the average height of the function you can find by taking the area under the curve and dividing it by the width of the interval. The value, f of c, given in the mean value theorem for integrals, is called the average value of f on the interval ab. Example 1. Let's find the average value of f on the interval from 1 to 4. So to do that, we're going to find the area under the whole curve and divide it by the width of the interval. So we'll find the area from 1 to 4 and then divide it by 3, which is the width of my interval from 1 to 4. All right, so let's go ahead and do this. If you find the antiderivative, you've got 1/3 x to the third minus x squared, evaluated from 1 to 4. So we've got 1/3 times, let's see, f of b minus f of a, which is 16. So that's the average value of f on the interval from 1 to 4. Now part B says, find the value or values of c guaranteed by the mean value theorem for integrals. In other words, where on the function is the height of the rectangle equal to the average value over the interval? Well, to do that, we'll take the average value over the interval and just set it equal to the original function, and we can solve for c. Do some factoring here, and we get two zeros, 8/3 and -2. But -2, see, that is not in our interval, so we'll take that one out of the running. So we know that in our function, when x equals 8/3, the y value of the function is equal to the average value over the interval. Example 2. In 2000, the world's population was 6.1 billion, and the relative rate of growth was 1.4% per year. This can be modeled by the function n of t equals 6.1 e to the 0.014 t, where n is people in billions and t is the number of years since 2000. Assuming this model remains true until 2050, find the average population of the world between the years 2010 and 2020. So we're looking for an average value in this 10-year period. So let's set up our integral. So 20 minus 10, that's the width of the interval I'm interested in. And then we'll find the area under the curve during that width. Pop that all into your calculator and you get 7.5316 billion people. That was the average population over that time. Couple notation problems here. Suppose C of t represents the daily cost for air conditioning your house in dollars per day, where t is the time in days and t equals 0 corresponds to July 1st, 2022, or whatever year. Explain what the following expressions represent in real-world terms, including units. So what do you think? From 0 to 90, C of t dt. That would be the total cost to cool your home for 90 days from July 1st, 2022. Now, what happens if we stick this 1 over 90 in front of it? It now becomes the average cost to cool your home for 90 days. Example 4. This one's kind of fun. At different altitudes, sound travels at different speeds. So we have a rocket flying at the speed of sound, but at different altitudes, and that is shown here in the piecewise function. So what is the average speed of the rocket? Interesting. Well, what we're going to have to do is find the total distance covered in each of these little piecewise pieces. So let's do that first. Good thing this is a calculator question. So let's see, between 0 and 11.5, okay, we've got 3,657, and then 3,097.5, and then let's see, 2,987.5, keep going, 5,688, and 9,210. Okay, so these are all distances in kilometers. And if we want to know the average speed, we have to take the total distance divided by the time. And the time for us is 80 seconds. So we get an average speed of 308 meters per second. And if we graph that at 308 meters per second, you can see it's right in the middle of all of that. So that's a quick introduction to applications of integration, but there's, so much more we can do with it. So I'll see you next time.